So this week we talked about the fundamental theorem of calculus, both parts. And the fundamental theorem of calculus is very important. Number one here deals with the second part, so I'll talk about that first. The second part of the fundamental theorem of calculus relates the definite integral and the indefinite integral. And it says that to compute a definite integral, to find an area, we can use an antiderivative and evaluate it at the two endpoints. So here we have this definite integral. We look back and make sure we wrote it correctly. So negative 1 to 2, 12x cubed plus x squared plus 3 with respect to x. So we need a function whose derivative is 12x squared plus x, or 12x cubed plus x squared plus 3. So we have a couple power rules. For x cubed, we get 3 plus 1 is 4. So a quarter x to the fourth. A quarter of 12 is 3. For x squared, power rule with exponent 2. 2 plus 1 is 3, so plus a third x cubed. And 3 is a constant. The first rule will apply. The derivative of 3x is 3. And the second part of the fundamental theorem of calculus says that we can use any antiderivative. So I'm going to choose the antiderivative where the constant is 0, because it'll give us fewer numbers to write. And here, we're evaluating from negative 1 to 2, and it's standard to just write that as a bar with negative 1 on the bottom and 2 on top. And what this means is we need to evaluate this at 2, and then subtract what we get when we evaluate it at 1. So what happens when we evaluate it at 2? Well, 2 to the fourth is 16. 3 times 16, 48. 2 cubed is 8. 8 divided by 3 is 8 thirds. 2 times 3 is 6. So this is what we get when we evaluate at 2. And now we subtract what we get when we evaluate at negative 1. At negative 1 to the fourth is 1. 3 times 1 is 3. Negative 1 cubed is negative 1. So we get negative 1/3. 3 times negative 1, negative 3. So what do we get? Well, I'm going to combine the whole numbers and the thirds. So with whole numbers, we have 48 plus 6 is 54. Those two cancel, so we just have 54. And how many thirds? Well, we have 8 thirds and negative 1/3. 8 third and a positive 1/3 makes 9 thirds. 9 thirds is 3. So we get that this is 57. Any questions about this one?
A little bit before you said, like on the second line, you wrote a +0 and then you erased it. What did you mean? Like, I didn't catch what you said.
Yeah, so the second part of the fundamental theorem of calculus says we can use any antiderivative to compute this definite integral. And remember, the indefinite integral gives a family of antiderivatives which differ by a constant. So right here gives all of the antiderivatives. We need to choose one of them. The most convenient one to choose is to choose the one where the constant is 0, because then you don't have extra numbers floating around down here. So I chose the one where the constant is 0. You could have chosen the one where the constant is 1 if you wanted. You'd have a +1 and a minus +1, which would cancel. But it's standard to just choose the one with 0. So that's what I'll choose. Any other questions about this one? Okay, next, part B. Integral from 0 to 2, 4x cubed minus 3x minus x to the half plus 1 with respect to x. So again, we're going to have some power rules here. And what do we have? Well, is that the same as the first one? Oh, no, it was a 12 in the first one. So here we have x cubed. 3 plus 1 is 4, so we get a quarter x to the fourth. 4 times a quarter is just 1. Here, exponent is 1. 1 plus 1 is 2. Half x squared times negative 3. Negative 3 halves x squared. For the next one, the exponent is a half. The power rule will still apply. A half plus 1 is 1.5, which is 3 halves. So we get x to the 3 halves. But then you divide by 3 halves. 1 divided by 3 halves is 2/3. And there's a negative there. And then 1, constant rule would apply. Derivative of x is 1. And in these, once you get to this step, you could check your work by taking the derivative here. The derivative of this function, 4x cubed, negative 3, x to the first, the 2 and the half cancel. Here, you just get x to the half with a negative because the 3 halves and the 2/3 cancel. The derivative of that is 1. And here we're evaluating 0 to 2. And what do we get? Well, substitute 2. 2 to the fourth is 16. 3 halves of 2 squared. 2 squared is 4. 3 halves of 4 is 6. And there's a negative. 2/3 of 2 to the 2/3. 2/3 of 2 to the 3 halves. 2 to the 3 halves. Yeah, you could write it square root of 8 if you want. You could write it as the square root of 2 all cubed. I'm just going to leave it like that, I guess. Maybe I'll write it as the square root of 8 in the next step. And then plus 2. Then you substitute 0. But notice here, when you substitute 0, you get 0 minus 0 minus 0 plus 0, which is 0. So combine all these numbers here. 16 and 2 make 18. 18 without 6 is 12. So yeah, I guess I'll write this 2/3 square root of 8. Or you can make it, minus 4 root 2 over 3, or you can make it, or you can even leave it like that, whichever you want. I've never deducted anything for square root, right, for writing a square root in a certain way. Any questions about that one? Okay, so in part B, notice it was a little more convenient in simplification than part A because this was a 0. And it's common, because of a problem like this, it's common for people to just ignore what happens at 0, because for a polynomial or for anything with x to numbers, positive numbers, you get a 0 upon substitution. But part C shows that you can't just ignore the 0. Why? Well, let's see what we get for part C. Integral 0 to 3 e to the x minus x. Sometimes you see these without parentheses. I always write them because, well, I don't do it necessarily for integration purposes, but this notation is a result of the rectangle approximation. And keeping this as some function times some x's makes it more clear in my mind how it relates to the rectangle approximation. Because the dx is another way of, well, it's an integral way of writing the change in x from the approximation. It's kind of a shorthand notation for the limit of the sum and the dx. So I always write them parentheses. So it's the entire function times the change in x. But what do we have here? We need a function whose derivative is e to the x. The derivative of e to the x is e to the x. And for that x, we use the power rule. 1 plus 1 is 2. So minus a half x squared. Evaluate this 0 to 3. And what do we get? Substitute 3, you get e cubed minus 9 halves. Substitute 0, what do you get? E to the 0 is 1. The other one you do get a 0. But e to the 0 is 1. So when we evaluate at 0, we do get another number. So e cubed minus 9 halves minus 1, negative 9 halves minus 2 more halves gives you negative 11 halves. Any questions about that one? Okay. Part D. Integral 1 to 2 x plus 1 over x with respect to x. Well, we can't just jump into the quotient. No quotient rule. What we can do is split this fraction. X divided by x is 1. 1 divided by x is 1 divided by x. So we haven't done an integral yet. All we did was break that fraction into 2 pieces. And now we can find antiderivatives piece by piece. Derivative of x is 1. 1 over x, well, the power rule wouldn't work there with x to the negative 1, but we do have the logarithm rule. And we're evaluating this from 1 to 2. And what do we get? Notice here, I did have to move this lower bound away from 0 because at 0, that's an end of, well, not end of a 2 months into Calc 2 integral if that's a 0. But we evaluate at 2, and what do we get? We get 2 plus the natural log of 2. What happens when we evaluate at 1? Well, we're subtracting 1 plus the natural log of 1. The natural log of 1, what is it? Well, e to the 0 power is 1. So I'll say, yeah, I'll just say 0, but that's 0. And now what do we get when we combine the numbers? 2 minus 1 is 1. Log 2 is log 2. Any questions about that one? And this was D. Okay, part E. Oh, that's going to be fun to simplify. Part E. Integral pi over 6 to pi over 4 of 4 sine x minus cosecant squared of x. We need a function whose derivative is sine. Well, there's also a 4 on there. So what do we have? How about 4 cosine? Does that work? What's the derivative of cosine? The derivative of cosine is negative sine. So that's not going to work. But if we throw a negative on it, the derivative of negative cosine is negative negative sine. So it is positive sine. And the 4 is still there. Next, we need a function whose derivative is negative cosecant squared. Well, the derivative of positive cotangent is negative cosecant squared. We're evaluating from pi over 6 to pi over 4. And there are some things you could do with these negative signs. You could flip the bounds around and make it 4 cosine minus cotangent. All I'm going to do, I'm just going to write it like this so that there are fewer negatives to deal with. So I'm just going to move the cotangent out front and still evaluate it. We didn't change anything, we just rewrote the sum. And we need to evaluate this. I think this will fit on this board. Evaluate at pi over 4, what do we get? Well, we get the cotangent of pi over 4 minus 4 times the cosine of pi over 4. And then we want to subtract the number that we get when we substitute negative, or that when we substitute pi over 6. So minus the cotangent of pi over 6 minus 4 times the cosine of pi over 6. And what do we get here? Well, we need some triangles. Sorry, that should be a 6. I think I said 6. Maybe I did. So substitute pi over 4, we get this. Substitute pi over 6, we get that. Subtract them. What is the cotangent of pi over 4? Well, first quadrant. Cotangent, well, tangent is opposite over adjacent, so cotangent is adjacent over opposite. The tangent of pi over 4, 1 over 1. So the cotangent of pi over 4, 1 over 1. So we get 1. What is the cosine of pi over 4? Cosine is adjacent over hypotenuse. 1 over root 2. Negative 4 of those gives us negative 4 over root 2. Where do I want to write this? I guess I'm going to write it at the top of the board. So what did this equal? 1 minus 4 over root 2. And now we need to substitute pi over 6. Well, pi over 6, pi over 3, pi over 2, 1 to root 3 to 2. The cotangent, well, tangent, adjacent, or opposite over adjacent, cotangent, flip that around. So we get root 3 over 1. And the cosine of pi over 6, what's the cosine of pi over 6? Well, cosine adjacent over hypotenuse. Adjacent is root 3, hypotenuse is 2. 4 of those, what would that give us? Negative 4 root 3 over 2. Notice the 2's cancel, so you're left with negative 2 root 3. Any questions about getting there? We have one more step, but any questions about evaluating those trig functions? Okay, so now we just have to combine numbers. What do we get? You can leave it as negative 4 over root 2. I'm not going to because it's, well, I think negative 2 root 2 looks better. But you can leave it as negative 4 over root 2 if you want. That's fine with me. Notice the root 3's do simplify. If you have 1 of something and you remove 2 of those, you're left with negative 1 of those. So we have negative root 3. Any questions about, which one was that? Part E. Okay, part F. We have some inverse trig. Part F, integral 0 to 1 of 2 over 1 plus x squared. Well, the derivative of inverse tangent is 1 over 1 plus x squared. So the derivative of 2 inverse tangents is 2 over 1 plus x squared. And we're evaluating 0 to 1, which gives us, you could factor out a 2 in this next step. I'm just going to not do that. Substitute 1, you get 2 inverse tangent of 1. Substitute 0, you get 2 inverse tangent of 0. And what do we get? Well, we need an angle whose tangent is 1. Well, we have this triangle right here telling us that the tangent of pi over 4 is 1. 2 times pi over 4 is pi over 2. We need next an angle whose tangent is 0 and is within the first and fourth quadrants. Angle 0, well, 4 angle 0, sine of 0 is 0, cosine of 0 is 1, 0 over 1 is 0. So the inverse tangent of 0 is angle 0. So we get pi over 2. So any questions about that one? Any questions about anything in number 1? Okay, so number 2, well, the first part of the fundamental theorem of calculus tells us several things which are important in math. And among other things, it tells us that every function has an antiderivative. One of the other things it tells us is that we can take derivatives of functions which are defined as definite integrals. And the Calc 1 computations using the first part of the fundamental theorem of calculus generally stick with that observation, taking derivatives of integrals and noting that the derivative and the integral almost cancel out. In the most basic sense, you can think of the derivative of a definite integral sort of being in the same mind as taking 2 and 1/2 and multiplying them. 2 and 1/2, you multiply, they kind of go away. Derivative and a definite integral, in a sense, kind of go away. They are, in a sense, inverse procedures, inverse operations. And in part A, we'll see that it looks just like doing something and then undoing it. But for the others, we'll see that it's a little different than that. So in the lecture, well, let's write this out first. For part A, f of x, integral from 1 to x, 1 over 1 plus t squared. X is our variable. And we want the derivative of capital F. Well, first part of the fundamental theorem of calculus, if the lower bound is a number and if the upper bound is just a single x, the derivative of this definite integral is the inside function of x. Any questions about that? So right here in the lecture, right at the end of the first lecture for this week, I mentioned that the first 2 problems on this worksheet could be done 2 different ways. So right here, I showed one way using the first part of the fundamental theorem of calculus. But this one, because we can take this integral with our rules, we can find this derivative directly, technically using the second part of the fundamental theorem of calculus. So I'll say, alternatively, we compute f prime of x directly. And I'll say using the second part of the fundamental theorem of calculus. What do I mean by this? Well, we can figure out this definite integral. Because the integrand, 1 over 1 plus t squared, one of our rules applies to that. The inverse tangent of t. And we evaluate from 1 to x. What do we get when we evaluate from 1 to x? I guess I could fit it here. Substitute x. Substitute 1. I'm going to put a box around that for now. So that's not our answer. That's just what f of x simplifies to by taking an antiderivative. Any questions about getting here, or any questions about what we're doing in this alternatively? So in this alternatively, we didn't find what we wanted yet. We just found f of x. Now we need f prime. Well, we can find f prime of x. Derivative of inverse tangent of x, 1 over 1 plus x squared. Derivative of inverse tangent of 1, well, inverse tangent of 1, it technically simplifies to pi over 4, but in particular, the inverse tangent of 1 is a constant, so its derivative is 0. So I'll say minus 0. That gives you 1 over 1 plus x squared, as we got in one step by applying the fundamental theorem of calculus directly, part 1. And also in this, in the statement of the first part of fundamental theorem of calculus, it does say that what that constant is doesn't matter, as long as the function is defined there. So you can see in here, that constant, that could have been a 4, it could have been a 20, because the derivative of any constant is 0. So any questions about either way we computed 2 part A? So you can use either computation you want. I might more recommend that one. But it is, I think, pretty nice to see, an example where you actually work through the integral. And we can also see for part B, an argument like that will apply. Part C, it won't, because we can't do that integral. So what does part B say? Find f prime of x for this function, 1 to x squared. Well, we'll do this 2 ways. I don't think I'll be able to fit both of these on the board. Well, I won't be able to. First, by the fundamental theorem of calculus. Well, the fundamental theorem of calculus will apply when that variable on top is a single variable, meaning a single x to the first, a single 1x to the first, I should say. So here, we can make a substitution which will reduce this integral to a function on which the first part of the fundamental theorem of calculus applies directly, meaning we can let u equal x squared. And what happens if we do that? Well, then f of u is integral 1 to u, 1 plus t squared with respect to t. Now, why do we do that? Well, now we can find df du, and we can find du dx. Du dx is 2x. df du, the first part of the fundamental theorem of calculus applies. 1 over 1 plus u squared. So now we want f prime of x df dx. I'll just say then f prime of x is df du du dx. So 1 over 1 plus u squared times 2x. And I'm just going to write that as one fraction. 2x over 1 plus u equals x squared squared gives you 4 total x's.
Can you move the camera down a little bit?
Yes. I think I'd do that naturally because I'm more likely to use the bottom of the board than the top, but so any questions about doing it this way, using a u substitution and applying the first part directly? So notice, and we'll notice this for part D and maybe part C. What does part C say? Yeah, we'll notice this for part C and D. Notice we could have gotten this in one step by using our chain rule observation, by taking an x squared and substituting everywhere we see a t, but then multiplying by the derivative of x squared. Now, just like previous uses of chain rule, if you have more than just a single x, treat it normally and then multiply by its derivative. And we'll use that observation for C and D. But before we get there, let's see how we could get this same answer without using the first part of the fundamental theorem of calculus. So I'll say alternatively, we proceed as in part A, alternative. F of x is, we can take that integral using the second part of fundamental theorem of calculus, the inverse tangent of t from 1 to x squared. Substitute 1 and x squared, you get the inverse tangent of x squared minus the inverse tangent of 1. And how do we do the derivative now? Well, then f prime of x, derivative of inverse tangent of x squared is what? 1 over 1 plus the inside squared times the derivative of x squared minus derivative of a constant is 0. And then, of course, this does simplify just like that did into one fraction, 2x, over 1 plus x to the fourth. Any questions about A or B? Okay, so parts C and D, we, well, part C, we can't do the integral directly because none of our rules will apply. But the first part of fundamental theorem of calculus does guarantee that that function inside does have an antiderivative. But for part C, what we can do is use a definite integral rule, which will convert that function into a function on which the first part of fundamental theorem of calculus does apply. So let's do that. C. F of x, integral. Oh, that's a typo. Good job. Wow, those aren't good typos either. I hope I didn't do that on the homework. Where did I put the homework? 1 second. Okay, I didn't make that mistake on the homework, good. These bounds should all be functions of x. If they're functions of t, it's not interesting because the derivative is 0. Well, on the homework, I didn't make this mistake, and on the test, I won't make the mistake. For parts C and D, the bounds should all be functions of x, not t's. I'm not going to ask you functions of t's, because that's, well, the derivative of that would be 0. So this one should say cotangent of x to 1. The last one should say x to log x. Sorry about that. That's a cube, isn't it? That is a cube. So move the camera down. I forget I did that. Okay. 2 minus 7t cubed over 4t to the 5th plus e to the t with respect to t. The reason t is even introduced here in the integrand is because x is already used in the bounds as the variable, well, as the variable which our function is a function of. So we change that to an x, but notice the first part of the fundamental theorem of calculus won't apply to this because the first part applies only when the bottom is a number and the top has x's in it. But we can rewrite this integral so that it is of that form. And I guess I'll write this on the next line. How can we do that? Well, flip the bounds, cotangent of x, leave the function alone. But this equal sign is not true right now, because if you flip the bounds around, the cost is a negative sign. So now it is equal. And now we can take the derivative as we did in part B. You could let u equal cotangent, but I'm going to use our shortcut observation for chain rule, where we replace all t's with this function and then multiply by its derivative, and we remember this negative sign here. So what do we get? We get 2, we get negative 2 minus 7 cotangent of x cubed all over 4 cotangent of x to the 5th plus e to the cotangent of x. So replace all t's with cotangent, leave the negative, but then multiply by the derivative of cotangent x. What's the derivative of cotangent x? Negative cosecant squared of x. And the only simplification I'll do is to just get rid of the 2 negatives. But you don't have to distribute that in. Just like with regular chain rule, sometimes it's nicer to see it, see the product split into its 2 pieces. But I will cancel those negatives because that's okay. And of course, you could write this cotangent cubed, cotangent of the 5th, but it's fine. So any questions about part C? No, that top isn't on the screen now. That looks like the entire board is there. Any questions about part C? Okay. Now part D, so part C, I made the integrand pretty complicated. Part D, I made the integrand a little less complicated, but I did throw variables on the top and bottom of the bounds, and of course they are supposed to be x, as in homework. And if they're t's, The derivative of the integral where I have those bounds as t's would be 0, because as far as x is concerned, that function is constant, meaning it's not a function of x. But so this one should be integral x to the natural log x 2t t squared plus 1 respect to t. And how do we do this? Well, first, notice the fundamental theorem doesn't apply to integrals of that form. We need a variable on the bottom, or a constant on the bottom and the variable on top. But we can break this integral into two integrals using our integral rules. What do I mean by that? Well, put some number between x and log x. Let's choose 1. 1's a perfectly good number. Now we have two integrals. But the first part of fundamental theorem of calculus doesn't apply to this first one because we have a number on top, variable on the bottom. The fundamental theorem will apply to this number on the bottom, variable on top. So in order to get the fundamental theorem to apply to this first part, we're going to flip it around by introducing a negative. Leave the second one alone because fundamental theorem applies to that. And now we have two integrals on which the first part of fundamental theorem of calculus does apply. Any questions about getting here? Some of you may be wondering about the number you choose. You could choose any number as long as the function and the bounds are defined at that number. I mean, so this is a very informal diagram. X and log x are variables, so these aren't fixed values. But you don't necessarily have to choose between these two changing quantities, meaning, you don't have to do any inequality argument to find something that lands between them in the most general sense of the word between. It could be a number over here or over here. The integral will take care of that. Meaning, if you interpret these using areas, that fifth part of the definite integral rules from lecture 12.2, I believe it was, that fifth part, you don't have to split between. Actually, maybe after this example, I'll say a little more about what I mean by that. Yeah, that'll be better explained with a specific example than one with variables. But now we need to do these two integrals, or the derivatives of these two integrals, and we'll do that using the fundamental theorem. This first one, we don't even need a chain rule argument because x is just to the first. But we do have to remember the negative. For the second one, well, replace all t's with log x. But then multiply by derivative of log x using the chain rule. Derivative of log x is 1 over x. And sometimes these do simplify nicely. This one actually does simplify a little bit, but you don't have to worry about that. I'm much more concerned with your application of the fundamental theorem than I am concerned with your simplification of it. So any questions about part D? number 2. Okay. So what was I saying about splitting the area? Well, I'll just mention that here. Well, yeah. I guess the argument with specific numbers doesn't work. With variables, it does work. Yeah, never mind. You don't have to worry about that. Now, the argument with specific numbers would get a little more detailed than I want to get. So, and it's not exactly true, but with variables, it would be true because of how the variables work. So any questions about 1 or 2? Okay, number 3. So before the fundamental theorem, the only way we could evaluate a definite integral was with the limit definition. And number 3 compares the two computations. So 3a, evaluate this integral 0 to 2 of 2x squared minus 3x using the second part of fundamental theorem of calculus. Well, second part, take an antiderivative, 2/3 x cubed minus 3/2 x squared. Evaluate 0 to 2. Evaluate at 2, what do you get? 8 times 2/3, 16/3, 4 times 1.5, -6. 4 times 1, yeah, okay, -6. And you get -2/3. Any questions about the computation in part A? Okay. Now, the limit definition we had in week, what would that have been? I think week 3, maybe week 4. Yeah, that might have been pushed off to week 4. I think the other applications of the limit were week 3. But how would that work? Well, we do the limit of the approximation using rectangles. Let n be the number of rectangles. So we're adding n rectangles together. It's a bad I. We're letting that number go to infinity. And what do we need? We need the base and the height of the rectangle. And how are these formed? I guess we're starting at 0. So we're starting at 0 here. And we're going to 2. And remember, the height of the rectangle is determined by the function. The base is determined by the x-axis distance. So what we really need to find are the points on the x-axis. We're dividing it into n pieces to form n rectangles. The interval is 0 to 2. So the base of the rectangle is the length of the interval 2 minus 0 divided into n pieces. So 2 over n. So what is the first x value? Well, we start at 0 and we go over 2 over n. What is the next one? We start at 2 over n. We go over another 2 over n. What is the next one? We start at 2 copies of 2 over n, and we go over a third. And the number of 2 over n's that we go over is taken care of by the sum. Then going from one to the next, what changes? Well, the 2 over n stays the same, but the number of 2 over n's changes. So what's the height of the rectangle? The height of the rectangle is given by the function evaluated at these. So evaluate the function at them. Let I be what is counting through the 2 over n's. The 2 over n's stay the same. What is the base? Well, the base is always length 2 over n. So we have the one side of the rectangle and the other side. Any questions about setting that up? Okay, so now we need to evaluate this. Well, how do we do that? Well, let's see. Equals the limit, the sum, and I'm going to write that first 2 over n out in front. And then we need f of 2I over n. F of 2I over n, replace all x's with 2I over n, so we get 2 of them squared minus 3 of them. And now we have some algebra to do before we can take care of the limit and the sum. So what does this inside simplify to? Well, 2 squared is 4. 4 and another 2 make 8. I squared is I squared. N squared is N squared. And over here, we just have negative 6 I over N. I'm going to go to the top of the board. And now, still not dealing with the limit or the sum, but I am going to distribute 2 over n. Two times 8 is 16. N and 2 more n's make 3 n's. 2 and 6 and a negative make 12, and a negative. N in the bottom gives us 2 n's in the bottom. Now, we could do some sort of distributing here, but I'm just going to, well, I'm going to erase this. So I didn't include these on this page. But you know, on a test, I would include the sums. I wouldn't have you memorize those. That's not worth memorizing. Right now that it's written like this, we can get rid of the sum of I squared and the sum of I. And how can we do that? Well, for the first piece, I'll take the 16 over n cubed, and then we have left the sum of I squared, which equals that. There it is, that minus. Yeah, I don't have these memorized. This one might be minus. I probably should have written that on this page. And then we have the sum of i's. We'll take out the 12 over n squared, and the sum of I is n and n plus 1 over 2. And now, all of that work, and we can now take the limit because we have degree 3 over degree 3, degree 2 over degree 2. We can use our coefficient argument. The coefficient on n cubed here is 16 times 1 times 1 times 2 over 6. The coefficient on n squared over there is 12, 1, 1 over 2, so 12 over 2. It gives us 8. No, it doesn't. It gives us 16 thirds minus 6, which does equal negative 2 thirds. And these are set up, at least for nice small polynomials, to parallel, at least in the end, the definite integral. Any questions about that one? Not that easy of a computation. This type of computation especially is one that I find much, much harder to do on lined paper than on lined paper. You know, if there were lines in here, there'd be too many lines. So any questions about this? Okay.
Will we be responsible for knowing how to do something like this on the final?
Yeah, that could show up. Yeah, so this computation, well, it wasn't on exam 1, but it could show up on the final. So you can see from part 3 how useful the fundamental theorem of calculus is, especially for one like this. Now just compare computation for part A to the computation for part B. Any questions about worksheet 13? Okay. So last week we didn't completely finish worksheet 11, and we do have some time now, so I am going to finish number 4 from worksheet 11. Worksheet 11, optimization. A cylindrical can with no top is to hold 8 cubic gallons of liquid. What dimensions minimize the cost of metal used to make such a can? Well, what measures the cost of the metal used to make such a can, a cylindrical can with no top? Well, the surface area of the cylinder with no top. So here this is worksheet 11, number 4. So here we're trying to minimize, should probably not spell calculus wrong, C-A-L-C. We're doing calculus on the surface area of this cylindrical can with no top. The formula for surface area of a cylinder, remember, is, well, it's the the part going around, which turns into a rectangle, 2 pi RH, plus the area of the top and the bottom. But the area of the top doesn't matter because it says that the can has no top. So all we need is plus the area of the bottom. A function with 2 variables r and h, but we're also given some information that the volume is 8. Volume is 8. So what's the volume of a cylinder? Well, it's the area of the base, pi r squared, times the height. So such that 8 equals pi r squared h. Any questions on getting those two equations. Okay. So these optimization questions, the calculus can get pretty detailed. And this one, it is pretty detailed. But the first observation is we have an R and an H. And we can use this function to get rid of an H. Because down here, H is a function of R. Solve this for H, meaning divide by pi r squared, and you get H equals 8 over pi r squared. Substitute that up here, and what do we get? Well, maybe I'll write at the bottom. So the surface area, which I'll just call S. So S equals 2 pi r times H plus pi r squared. And what does that simplify to? That does simplify a little because some pi's will cancel and an r will cancel. 2 and 8 makes 16. Pi and pi cancel. R over r squared simplifies to just 1r in the denominator. So any questions about getting S in one variable? Only variable is R now. So now we can do our calculus since it's one variable. I'm just going to rewrite that up here. I'm actually going to write the pi r squared first. So we have our surface area function. So let's find its derivative, let's find where it's 0, and then let's show that that gives a minimum. So S prime is what? Well, derivative of r squared with respect to r, 2r. Derivative of 1 over r, negative 1 over r squared. So negative 16 over r squared. We want where this is 0 and where it's undefined. Notice it's undefined when the radius equals 0, which isn't going to form a cylinder. So I'm not even going to consider that. We need to find where this is 0. When 2 pi r equals, bring the negative 16 over r squared to the other side. Solve this for r, and what do we get? What do we get? Multiply both sides by r squared. 2 pi r cubed equals 16. Solve this for r. Meaning divide by 2 pi. 16 and 2 make an 8. Pi is still in the denominator. So we get r equals the cube root of 8 pi, 2 over cube root pi. Just going to say the cube root of 8 over pi. And of course, the cube root of 8 is 2, but that's fine. Any questions about finding our potential choice in R? Okay. So now we have to show that this does give a minimum. And you could do a decreasing, increasing argument using the first derivative, looking at both sides. I'm going to use the second derivative again because I like that computation more. What's the second derivative here? Well, 2 pi r is a function to the first power. The power rule will tell you the derivative is just 2 pi. How about 16r to the negative 2? Derivative of negative 16r to the negative 2 is positive 32, r to the negative 3. And at that r value, 2 pi is constant, r cubed is constant, so 2 pi plus 32 over those r cubed is positive when r equals the cube root of 8 pi. So r equals the cube root of 8 over pi gives, well, that means it's concave down. So that means the critical point will be a minimum. Any questions about reaching that conclusion? Unfortunately, we're not done, because that doesn't answer the question. It doesn't say what radius minimizes it. It says what dimensions minimize it. So we also need h. So what is h? Well, h was given by 8 over pi r squared. So if you had one like this on the final, I wouldn't want you to spend your time simplifying this. So I'll just say equals 8 over pi times 8 over pi square and cubed, or square and cube would make 2/3. So I'll put a square around this as something you could leave as your answer, but I will show you that it does simplify. How does it simplify? What, 2 over cube root of pi, is that right? Am I counting the number of 8s properly? So pi, we're left with a cube root of pi in the bottom. And yeah. So on a test, if you had one like this, you could leave your answer in that form, that's fine. But this one does simplify pretty nicely, actually. Yeah, okay. So any questions about that one? Optimization questions could get, some of the details could get pretty, well, it could require some care. Like the last one in the lecture we did where the similar triangles showed up, that one I would consider on the same level as this in terms of organizing the details. So any questions about that worksheet 11 problem? Okay, so let's see, the rest of this class, there is one more topic for next week. The lecture, I think, is about 26 minutes. There is a homework assignment due next week. I tried to make this last homework assignment a little shorter than the others. Hopefully you interpreted this homework assignment as a little shorter than the others. It's all on the fundamental theorem of calculus, the 2 parts. So there is the one more topic for next week. That topic there won't be homework on that topic. There is a worksheet with one problem. So next week, well, what's today? Today's Thursday. Tonight, I will post that video and next week's worksheet. And next Thursday, we will go over that one problem on the worksheet. But I am going to post it tonight in case some of you would like to get slightly ahead for the last week in this course. Or it's more just so you have a better idea of how to orient yourself in terms of final exam preparation. The final, I checked yesterday, it said the final is Friday the 21st? Yeah, today's the 6th. So final is Friday of finals week, which is May 21. It said 12 to 3. I will have the final exam posted from 9 a.m. and then I'll put a due time of 3 o'clock on it, I guess. Maybe a little later. But it will be that Friday. So for the next 2 weeks, it would be a good idea to start at least thinking about the final exam starting this weekend. Later today, I'm gonna post the last lecture. I'll post the worksheet. We'll go over that worksheet next Thursday. But I'm also gonna post something called homework and exam review. So for this class, there are gonna be 2 different review documents. One will be called final exam review, and I'll post it next week. One will be homework and exam review. And it will contain problems similar to the most missed homework and exam problems. And that will be posted later today. And we will go over that on Thursday of next week in addition to worksheet 14. And there will also next week be final exam review posted, which covers more than just the most missed problems. Well, we won't go over that here, but I will give you solutions to that a few days after it's posted. And all of the information I just said will be contained in an email, which I've yet to write, but I will write it. And also, I might have mentioned this. Sometimes I forget if I mentioned something or if I just thought of mentioning it. I will send a list of all the topics that will be potentially covered on the exam. It'll be most of the semester. There will be a couple topics which are not on the exam, and I'll tell you that. So later today, you should expect 1, maybe 2 emails from me, probably 2. One with week 15 information or 14 information, and one with final exam information. So are there any questions about anything I just said? Okay, well, I hope you enjoy your week.